We have artificial intelligence that can write sonnets, pass the bar exam, and generate complex code in seconds. Yet for decades, if you asked a machine to fold a shirt or pick up an egg without dropping it, it would fail. Roboticists call this Moravec's paradox. The cognitive tasks that feel incredibly difficult to human beings require very little computation, while the sensory motor skills a toddler performs effortlessly, like walking or grasping, demand enormous computational power. This diagram illustrates the intersection where that barrier is breaking down. This overlapping space in the center represents embodied AI, or physical AI, where software agents equipped with reasoning capabilities are integrated directly into physical machines. This chart shows the projected exponential growth of the embodied AI market, expected to hit $8.7 billion by 2033. Factoring in the broader hardware and software ecosystem, analysts are preparing for a $500 billion industry. The transition from isolated lab prototypes to active commercial pilots on actual factory floors is aggressively scheduled for the 2025 and 2026 production window. Through breakthroughs in multimodal processing, intelligence is permanently stepping out of the screen and into the real world. To understand how a robot processes reality, we have to look at the brain of the machine, Vision Language Action Models, or VLAs. This diagram maps the physical AI technology stack. The Understand and Adapt nodes reveal System 2, interpreting scenes and formulating plans. Once set, System 1 takes over, translating those thoughts into fluid motor actions via diffusion transformers, 120 times per second. NVIDIA's GR-OOT-N1 is a leading example of this dual-system architecture. It splits the cognitive workload, reasoning about an objective at a deliberate pace, while managing the rapid, reflexive muscle movements required to execute it. Because perception, reasoning, and motor control are unified, engineers no longer need to write rigid, hard-coded rules for every possible scenario. When a robot encounters a novel physical problem, it dynamically calculates and executes a physical solution in real time. This pyramid illustrates how models are trained safely using a base of internet data, a middle tier of synthetic simulation, and a peak of real-world teleoperation. That middle tier uses digital twins, where AI trains synthetically, exploring edge cases at 1,000 times reality speed. After millions of virtual iterations, these VLA brains are downloaded into physical hardware ecosystems built to house them. Figure 02 has deeply integrated its hardware with OpenAI. On a BMW manufacturing floor, workers give natural language commands, and the robot parses the speech, understands spatial relationships, and executes the physical work. Concurrently, Elon Musk has directed Tesla's massive auto manufacturing infrastructure toward the Optimus Gen 2 program. Leveraging existing supply chains and autonomous driving networks, Tesla aims to drive the per-unit cost of a humanoid robot down to $20,000. Beneath all of this sits NVIDIA, acting as the underlying infrastructure provider. They supply edge compute chips like the Jetson Thor, running massive transformer models natively inside the robot's physical body, eliminating the need for constant cloud connections. Advanced battery density, pinpoint actuator precision, and local compute power have aligned. Physical bodies are now economically and technologically ready to deploy simulated intelligence at scale. Control over physical AI now directly correlates with national industrial capacity, creating a fierce competition between global superpowers. The United States strategy is defined by deep technological integration, stringent safety protocols, and the development of proprietary foundation models, driven by companies like Boston Dynamics, Figure, and NVIDIA. In contrast, the Chinese strategy relies on a lean methodology. Manufacturers like UTech and Unitree emphasize rapid hardware iteration, severe cost reduction, and immediate mass-market deployment. Across the globe, the industry is crossing the critical threshold from Phase 2 pilot programs into Phase 3, which is active, fleet-wide production. Humanoid robots have moved past high-end research and are entering the economy as a general labor commodity. Intelligence that merely calculates and predicts is becoming the baseline. Intelligence that acts in the physical world is the new frontier. Check out the Learn by Doing with Steven YouTube channel and other platforms to master tomorrow's tools. And listen to the Steven Data Talk podcast on YouTube Music, Spotify, and other platforms for deep dive discussions on data and AI. Links are in the description.